So we're to talk about the business end of combat robots, but before that, we need a little bit of lesson in safety. My transmitter is off right now. So what you just saw there was a good example of a fail-safe fail. Now this is a great way to not be allowed to compete in a competition because you won't make it past the safety check. And yes, there's no weapon on there, so don't freak out. I'm not doing something too stupid right now. But, so what you want to do before you actually start putting anything that spins violently, even if it is just a test version of the weapon, not the real thing, you want to make sure your robot can actually pass that safety check. Alrighty, so by the way, I'm Jason, the creator of the Tabletop Battlefield and Team Rocket Robotics. That's a long-winded intro. And what we're doing by the title is filling in this missing gap right here. We're going to create a 3D printed version of the final weapon just to test sizing and make sure everything works before I spend the money on some nice high-quality laser cut pieces for the weapon blades. The first step is to assemble the prototype cage that goes around the weapon. Because what we need to do is build the weapon shaft next. So all you really have to do is build a shaft that essentially holds itself in place. So I'm measuring the length of it to be a little bit longer than the brackets are spread apart here, because I'm going to have some extra space on either side that I'm going to file down a little bit and drill some holes for some basic pins. Now yes, drilling through your weapon shaft does compromise it a bit, but these pins are on the outside of the robot mounting points. They're not near the spinning thing, and they are not taking the brunt of the impacts when your weapon is basically beating the crap out of the opponent. So these small limitations or small reductions in strength on those areas of the weapon shaft will not be a serious issue. And then comes the important part where you take the shaft and make sure that the weapon bearing you're going to use actually fits on it, and discover that it doesn't. Apparently this particular 1/4 inch diameter stock that I bought is not actually a 1/4 inch. It's a tiny bit bigger than that. Alright, let's try it again with a proper sized piece of steel. So now it's time to move on to the final design of the weapon. I'm saying final design because a lot of the basics of the weapon system here I actually designed, or laid out, maybe a better word, back in, I believe it was episode 2 of the series, where I talked about kind of rapid prototyping the entire robot. So at this point I'm working on final details, like the exact sizing of the pulleys on the pieces, what they're going to look like, where the details of the pulleys are going to be placed, bolt positioning for holding the whole thing together, also approximate final length of the actual weapon blade, because the end goal here is to have a 3D printed copy of the final weapon system, because I want to make sure... Is the robot still on? The robot might still be on, actually. Thank you, receiver, for telling me that it was sitting there not doing anything. It scared the heck out of me. I may also be slightly on edge because there's a risk of tornadoes tonight. And the warning siren that's on my bedroom in there, attached to my weather radio, will probably go off at some point while I'm recording this show. Let's 3D print up our weapon pieces here. There's our mocked up weapon pieces, and see how they fit on the robot. Now before I can do any further testing on the robot, there is one more thing I have to build, and that's spacers. The thing about having a dead shaft is right now the weapon can basically slide back and forth to the left and right because there's nothing keeping it in place. So what I wanted to do is, once I got this on the robot, I could actually measure the spacing between the various pieces of the weapon as the edge of the brackets. I can now go back in the blender here and model up a couple 3D printed spacers, which will not only keep the weapon relatively in the center of the shaft, but also importantly, it's going to hold the bearings in the weapon assembly. I'm just about ready to go ahead and start testing the weapon. I'll talk about safety in a moment. Just hold on, guys. Just 1 minute. First thing before I do that, I want to make sure the weapon motor itself works. So I'm going to run some basic tests on the weapon motor while it's not hooked up to the weapon. This is also just a basic mechanical test to make sure it's not going to rip itself apart. See how stable the pulley is on the end of the weapon, I guess, weapon shaft. Yeah, we'll say that. And also let it run for a while because I want to see if the ESC that's driving the weapon is going to be heating up at all. We don't want it to, but it always, man, that can happen. These are like drone and airplane ESCs, which really like to be flying through the air for cooling and not shoved in a stuffy robot getting thrown around. Let's see how it works. The weapon motor test looked pretty good. I ran it for about 30 seconds in total, checking the temperature, and by that I mean putting my finger on the ESC and seeing how it goes, and everything went great. So awesome. Before we can actually obviously drive the weapon, we need a belt to go between the motor and the weapon. I like using my own custom printed TPU 95A drive belts. The advantage of doing this is that you can get the exact size of drive belt you need. Whereas if you buy a pre-made one, they often come in set lengths. You kind of have to design around that. In this case, you don't have to. You can literally measure what size of drive belt you need, model it up, and 3D print it out. Now, the downside of using TPU 95 drive belts is that they do wear out over time. It's a material that slowly stretches out, and it'll hold that new position later on. Now, how much it stretches out depends on the thickness of belts and things like that. So what I would recommend is getting an idea of how long it takes for that belt to stretch out and eventually fail, because once it stretches out a bit, it's going to come off and your weapon's going to no longer work. So you want to get an idea on how long that takes and just have a bunch of these printed up and ready to go for an event. Now, when it comes to calculating the actual size of the drive belt, there's a very simple way you can start. And I say start because it's not an accurate way, but it's a good starting point. Now, figure out half the circumference of the pulley around the weapon, half the circumference of the pulley around the motor, and then add 2 times the distance between the center of the pulley on the motor and the center of the pulley on the weapon. And that will approximate inside circumference of the drive belt. So what you do then is build a cylinder here in Blender with a whole bunch of vertices, like 256 or something. And you set that radius, do the math to figure out what the radius of the inside would be, and you can circumference the radius, whatever that is. Circumference divided by pi is diameter, diameter divided by 2 is radius. And then take that radius, add the thickness of the belt to that radius, and create a cylinder in Blender doing that. Then create a second cylinder that's just the radius of the inside diameter, which is the one that figured out how big your belt needs to be. Do a Boolean operation and cut it out so you have just a nice outside ring with an inside diameter of the belt diameter you want, and the outside belt diameter factors in the thickness of the belt. Now, this gets you close. It's probably not going to be correct. It's often a little bit on the small size, but it gets you a little bit close. It actually might be on the big size. It kind of it depends on how much approximation you do. So what I end up doing is printing off this belt and then a few sizes bigger and a few sizes smaller. So I just go into Blender and I scale it up by maybe 10% and 20%, and then I also scale it down by 10% and by 20%. And then I print all those up. They only take a few minutes each to print, and I figure out which one fits the best. If I need to, come back, make some more adjustments, and repeat that process until I get a tight fit. And once I know that is what it is, I save those changes in Blender, and I've got the model I can print off as many times as I need. Now we're on to the part about talking safety, because we're getting ready to spin up the prototype weapon, and even though it is a prototype, it's got elements of the real weapon in it, the bearings, the shaft, things like that. And granted, a probably violently exploding piece of PLA isn't as dangerous as a violently exploding piece of metal. You still don't want to be anywhere near it. That can probably jack up some eyes, skin, things like that pretty easily. So I am following basic safety procedures, guys. And if you're worried about people getting hurt with these robots, and I don't know why, maybe if you're worried about the government getting involved because someone hurts themselves with a robot and they want to regulate these things, maybe you're just secretly a libertarian. There are other political ideologies in this country, guys. Trust me on that. And libertarian is one of them. And now that I've offended 99% of the population of this country with my political commentary, let's talk about what safety procedures I followed for this robot. So my armored box is not working at the moment. It has no floor and no ceiling, so that's kind of out of the question for testing. So the other thing you can do in terms of keeping yourself safe is get yourself away from the robot. Put something between you and the robot. In this case, off to the side, never show it, I've got a storage room I can walk into that's got a wall, a door, all sorts of stuff I can close up, so I have no direct line of sight to the robot, and I should be relatively safe to test from there. And I got my camera running, so I can go back and review the footage. Let's see what happened. What's happening here is the weapon blade, it's technically smaller than the diameter of the wheels, so it can do a full 360-degree spin, but it's like a millimeter shorter. The radius of the weapon's like a millimeter shorter than the radius of the drive wheels. So any imperfections in the floor, it's going to hit those, and that's what it's doing. It's sitting on a part of my workbench where there's a bump, and it's like, you know, it's grinding into the workbench. That's not good. So let me fix that. I'm going to go back to Blender here. I'm just going to reduce the size of the weapon by about 2 millimeters. Alright, so the robot's in the same spot it was. I can actually see the marks in my workbench where the weapon was chewing into it. So I know that I'm sitting in the spot where the high floor was, and I'm going to follow the same safety procedures. I'm going to leave the room. I got the camera running to record what happens, and we'll throttle up the weapon and see how things go. And that time, the weapon test went a lot better. So hey, I think we're looking pretty good in how things are coming. I like the size of the weapon. It seems to work. I did end up doing one more test a little bit later where I let the weapon spin for about 2 minutes. I came back and I checked the temperature. Once again, I put my finger on the speed controller and it felt all right. So at least with the dummy weapon, it's not overheating itself. That may change when we get the proper steel weapon on it, but we'll figure that out a little bit later. Now, the last thing I had to do today is make sure that this whole contraption I've just built actually will fit in the final version of the robot. And you know what that means? Spreadsheet math, everyone's favorite part. That's why I saved it for the end. 9 grams. 2 grams for the weapon pulley, and then finally the weapon shaft, 16 grams. What I got going on over here in the second column is that I've got the total weight of the robot as is, a mathematical offset for certain basically components like the nylon chassis and things like that. And then I've got, in addition to that, all the mass of the parts of the robot that are not currently in the robot but still need to be added. And originally I had a few too many components that were not in the robot, but they actually are in the robot now. And the entire thing ballooned to like well over the weight limit, which was very, very bad. But when I did some recalculations, we're at like 446 right there. We're getting close. We're still under by about 10 grams, 8 grams, which is good enough for right now. But the last critical component is going to be the weapon blades, which are currently listed at 28 grams. But to get the proper mass, I got to jump into Blender and do some math. So let's do that right now. In Blender, I've got selected one of the weapon blades, and I'm using a 3D print extension for Blender that will go ahead and calculate the volume of the 3D objects. Now, it's really huge. It has to do with the fact that Blender is actually working in meters, where I'm using is millimeters. So what you want to do is take this number and divide it by 10 to the 9th, and that'll get you the actual volume of the piece in cubic centimeters, which in this case is about 1.28 cubic centimeters. We know that steel is approximately 7.9 grams per cubic centimeter, so this individual blade comes in at a little bit over 10 grams. Two of them combined is going to be about 20 grams. So I think it's 20.2 grams is what I added up to. We go back to our spreadsheet and things are looking pretty good. Okay, I'm not going to show you the spreadsheet again. I've done that enough. Alright guys, well that is the workflow here for rapid prototyping your weapon for your combat robot. Of course, I believe you're capable of doing things safely on your own. So, thank you guys all for watching. Once again, I'm Jason, the creator of Team Rocket Robotics. Hit that subscribe button if you want to see more videos about building combat robots. I'm going to get back to Microflash at some point when I'm done with this guy. And also, if you like the occasional random commentary about how people are good enough to be responsible for their own lives. It was done in a somewhat joking manner. Okay, guys, have a great week.